So if you were designing a study and you've gone through, the first part is you got to, what you need to do is you develop your research questions, you select your study design, you choose what variables you're going to help you answer your research question and what level of measurement those variables are at. You write up your analysis plan, and you calculate the sample size you might need to answer your question and have enough power. Then once you're done with the study, you're going to collect the data, you're going to code it, and you may enter it into a database, clean it up, check for outliers, check for problems. You may create new variables. You may run univariate, where you're just doing some simple descriptive statistics or looking at relationships in your demographic variables, looking at correlations to help you identify which variables to include in your model to help answer your question. You're then going to refine your model, maybe add or delete predictors, look at your assumptions and test those with the different tests that the software packages provide. Go through, check them again, and then you're going to make some interpretations. So here's an example. An investigator hypothesizes that atelectasis formation during general anesthesia is predicted by, you can see the variables listed there. So the outcome in this case is atelectasis, which maybe is quantified by a chest x-ray. And you can see a number of predictors there. BMI would be continuous. Surgery type would be categorical. Duration, continuous. Smoking, categorical, actually nominal, binary, yes or no. Comorbidity, maybe that's ASA class, so that could be ordinal. And gender would be a nominal variable. And so if BMI was found to be a significant predictor, then its regression coefficient would be adjusted for the other predictors that were included in the model. It's an important concept to understand. All right. I included this paper in your readings this week that you can refer to, and we're going to go over it for the next few slides. All right, so this was a study that was done in Japan, where they're looking at factors affecting extubation time following pediatric ambulatory surgery. So it was a retrospective cohort study, meaning they identified a group of children and looked back in their medical records. They're not comparing it to a control group. They gave us their sample. So these are ASA 1 and 2 children who had surgery of less than 2 hours at a university hospital in Japan. You can look at their inclusion and exclusion criteria, which helps kind of make it a little bit more, tightens up the sample. You got to think about, would this be applicable at your institution? Exclusion criteria is helping get rid of those things that might bias the results. They're only interested in extubation times, so mask anesthesia would not be applicable, nor would deep extubation. And they wanted to get rid of sick kiddos that could cause some confounding a bias in their results. And that was their outcome. And you can see the predictors that they looked at. And we have the results over here, and then their demographics listed here. All right, so here are the results. Feel free to pause the video and take some time to look through this and cross-reference the manuscript I included for you. Okay, so right here, their table 2, it actually tells us, it gives us enough information without even having to refer to the paragraphs. Right there, that's our time to extubation is our dependent variable. Our predictors are listed here that they included. Inclusion of all variables allows for adjustment of the regression coefficients on each predictor for the outcome of interest. Okay. Here we see the parameter estimates, and then their t-values and their associated level of significance. So these would be our beta coefficients. This would be our intercept, and these would be our coefficients here that they included in their model. All right, this shows you what they found. So here's their estimates. What they found was only 2 of the independent variables were predictive, which was mean body temperature and mean end-tidal CO2. And what they were negative relationships. That's why we see that negative sign there and negative sign there. You can see they're 2 significant variables right here. Okay, so what they're saying is for every 1 degree increase in body temperature, you would expect time to tracheal extubation to decrease by 3.5 minutes. And in end-tidal CO2, for every millimeter it goes up, you expect it to go down by that much. So if we just adjust it to make it easier to understand, is for every 10 millimeter increase in end-tidal CO2, you expect the kids to wake up about 4 minutes faster. And then if you were actually to plug that into a regression equation, this is what it would look like. And then you would actually enter in actual values that were within the estimates of the ranges that you may have suspected or had in your particular study to predict maybe an individual patient's results. So what the results suggest was that delayed anesthesia emergence may be prevented by avoiding a lower body temperature and end-tidal CO2 in pediatric patients. They said may as opposed to cause because this was retrospective. It was prone to some biases. It could have errors in recording. They didn't control for anesthesia provider effect on the outcome or type of surgery. The sample size may have been small, so it may have been underpowered, so maybe they didn't have enough power to find some of the other predictors. You cannot establish causality because it was retrospective, only suggests an association. And also you can see that they didn't report the units of measure and timed extubation. It was assumed that it was in minutes. That was just something I picked up on. All right, here's another one. You guys can take a look at the article and you can skim through it, read through it. I paid particular attention to the statistical analysis plan and results section. Okay, so this one was looking at factors related to blood loss after femoral neck fracture. And they were primarily quantifying that, then they were also running some predictions. So it was a prospective cohort study in Uganda. And they wanted to look at the amount of blood loss and what were some predictors of that. Okay, so here's their statistical methods section. You can see here where they're talking about they looked at the how they examined normal distribution of their variables. And then they describe how they categorize some of their variables. So what they ended up doing is some dummy coding of these variables to include them in the model. Okay, and then what they did is they're explaining what their results mean in per unit change in the variable. What they did is an unadjusted and adjusted model. So when they did their unadjusted model, what they did is they ran multiple individual linear regressions, meaning just one independent variable predicting blood loss. And then they only included those with a p-value greater than 0.15 in their final model. And then they established what their level of significance was. So here's the results. So you can see here they have their unadjusted regression coefficients listed down this side. And then the adjusted, this is, so you can see what happens is when they included male gender by itself, but then when you control for the other variables, the regression coefficient, it goes way down so it has minimal impact. Likewise, you can see some differences in, even though they're not significant, you can see what impact it has on the coefficients included in the model. The only two that they found was use of diathermy, which is cautery, and this was a binary variable, meaning they're referring it if yes and they're referring to no. So this is a coefficient if yes they use cautery. It decreased blood loss. And in fracture type, we can see differences that meaning a type C resulted in more blood loss than a type B. And these were individually compared. So this is type B compared to a type A fracture, which is probably the least complicated of fractures. And then they have their constant or their y-intercept down here. So then they show you that they did some regression analysis, identified some significant correlations, but that their final model only identified these two variables here. And they go on to explain what they found. So, and you can read through that. So, for example, if they look at blood loss for type B fractures, what they would say is that amount of blood loss would equal the constant plus 1.05 times the amount of blood loss that occurred for type A fractures. And you can see so on there. So what this tells you is this means that for every unit blood loss in the perioperative time for a fracture type A, there was a this amount of increase in blood loss for those other two. And you can see here they drew some conclusions that there may have been differences in blood loss based on surgeon type. They didn't really control for transfusion triggers that could have impacted the treatment. And then they drew some conclusions there. So I hope this was helpful. If you have any questions, feel free